we started talking about the Portland cement. And we said that the Portland cement was actually started or found very long time ago, about 1800s, somewhere in UK, and it was a combination of gypsum and limestone. And we also talked about different types of cement. We said cement plus water is going to be cement paste. And if you have sand in the mix, it's going to be, call it a mortar. And then if you have a mortar, basically cement plus water, then instead of sand, we also have aggregate or gravel. Then we can call this concrete. So again, I wanted to emphasize this as that a lot of people confuse concrete for cement, but we as civil engineers, we should not do that. And we make sure that we are not using cement instead of concrete. I've seen many students doing that, so please make sure that we know the difference between concrete and cement. And we also talked about the different percentages of Portland cement in the mix. That we said Portland cement is 7 point. I'm not going to write this because these are just a review of the last session. So Portland cement, and by cement we said that you're referring to Portland cement. So Portland cement is going to be 7.5% to 15% of the volume of the mix. Then we have water based on the water to cement ratio. Then we have aggregates, which is both sand and gravel. That would be majority of the concrete, about 60 to 75% of the volume. And then there's one other component that is air voids, which is about 1 to 15% by volume. And we are considering air voids in the mix because we said that this affects the durability of the concrete, and we definitely want to have air voids. It's not that it's a bad thing for concrete. We want to have air voids in the concrete. And then we also mentioned that we're going to have some sort of chemical admixtures in the mix based on the type of properties that we want to enhance in the mix. So we're going to talk about those later on. But let's talk about, so I'm going to move over here. Let's talk about the Portland cement production. Okay, so how do we produce Portland cement? I'm probably going to attach a link on Canvas to a video for a cement production plant that you can clearly see the steps and the diagram that shows the production steps for the Portland cement, but we are going to talk about these steps briefly here, and then you should be able to see the graph and also the video on your Canvas course page. So the first stage is crushing and grinding of raw materials. We want to get raw materials then crush them and grind them, and of course sieve them to make sure that we have the correct combination of the materials that we want. Now these materials are calcium oxide, which is a calcium-based material, and that includes limestone, chalk, and, or probably not and, or oyster shells. Okay, now we have to have a calcium type material in the mix of the cement, and also we need to have silica and alumina. So we need these for the chemical reaction to produce and make the Portland cement, and later on we need the silica and also the calcium part of the Portland cement to be able to react with water and does the hydration process for the concrete. So you also have silica and alumina. That includes clay, shale, and also a type of material that we call it blast furnace slag. Now we're going to talk about the slag later on. This is a sort of we will review slag later as material. And by cementitious material, we mean that a type of material that is not necessarily Portland cement, but it can react with water and does the chemical reaction and show a cement type or Portland cement type reaction in the mix, but it's not necessarily Portland cement. So we're going to talk about that. So once we have these two types of materials, we can go ahead and heat them and melt them in a kiln. So heat and melt. In a kiln at a very high temperature at 1400 to 1650 degrees Celsius, which is around 2500 to 3000 Fahrenheit. And then a product of this process is called cement clinker. So cement clinker is sort of pieces of materials that later on we break them and sieve them to get the Portland cement in the form of a powder or powder Portland cement. And sometimes, or most of the times, in terms of production, when they want to show the capacity of the production capacity of a Portland cement plant, they show or they specify that in terms of how much clinker, how much cement clinker they can produce in a day or in a month. Okay, so and then the last step after producing the clinker will be we need to add gypsum to the mix. So adding gypsum. What does gypsum does is that it delays set time. It means that it's not going to set instantaneously, and when you add gypsum, it'll delay the set time for the concrete. So we need to add gypsum to and pulverize fine powder. Now, when we talk about the fine powder, it is 7 times 10 to the power of 11 particles per pound. That's a lot of particles per pound, and it shows how small the cement powder will be in the mix. Right? And then the reason we need that the Portland cement powder should be that small or that fine is that we want an increased surface area. So small particles provide increased surface area and more surface area means more hydration. So once you have a much more surface area or contact area that can contact the water molecules, you should be able to see more hydration from that process. That's why we need a very fine particle in our final cement production plant. So I'm gonna insert, when you look at the, let's see, okay, so when you look at the lecture notes, I should be able to insert a diagram of the Portland cement production. So this is going to be Portland cement production. So when you look at the notes on Canvas, you should be able to see the diagram and also probably a link to a video that shows the production process. Okay, so that's pretty much all you need to know about the production. And then this is also important. We want to know what is the chemical properties or the chemical composition of Portland cement. And sometimes we refer to Portland cement as PC. And we are concerned about the chemical composition because the type of the hydration and the chemical reaction between the different components of the Portland cement is really important and affects the process and also the properties, the short-term and long-term properties of the concrete. First thing you need to know is that the main components, what are the main chemical components? The first one is the tricalcium silicate. So tricalcium silicate, C3S. Then we have dicalcium silicate, which is C2S. This is going to be a short review, not the review, but it's a short flashback to chemistry, which I'm pretty sure not all of you probably remember a lot from chemistry. But anyways, we don't want to show the actual chemical reactions, but we just want to show what type of chemical components we have in the Portland cement. And then we have the tricalcium aluminate. So tricalcium, which is C3A. And then we have tetracalcium aluminoferrate. So tetra. And this is C4 AF, both a combination of aluminum and calcium. Okay, so these are the major components or the main components. And then we have some minor components in the mix or in the powder as well. So minor components. These include magnesium oxide, magnesium, and then we have titanium oxide, and then we have manganese oxide, we have sodium oxide, then we have potassium oxide. You also need to know that alkalis, um, as such as Na2O and also K2O, they react with silica and they cause disintegration and expansion of concrete. So they cause disintegration and expansion of concrete, which we don't want to happen, right? And something to mention here, there's a famous phenomena in concrete that is called alkali silica reaction, or it's called ASR. And this is very important when you study the properties of the concrete, because it affects the durability and also the performance of the hardened concrete after you cast the concrete and after you build the concrete the structure. The ASR, or the alkali silica reaction, is very important, that might affect the properties of the structure. So we're going to talk about this also later on. Okay. And there are some examples of different effects of the ASR on the performance of the concrete. It can generate, or it can produce surface cracks. And of course, disintegration we already mentioned up here, right? Okay. So I'm gonna also insert a picture of ASR in concrete. So you will see what will be the effect of ASR in the finished concrete surface, right? Okay. So now that we know a little bit about the production, we can go ahead and talk about the estimation of the properties in the lab. The first, so the lab, yes, the lab tests estimate cement properties. Okay, so the first property that we want to estimate in the lab is the fineness of the concrete, not the concrete, the fineness of the Portland cement. And with the fineness test, we basically want to know how fine our cement particles are. And these are indirect methods, because you cannot, if you want to directly measure or estimate the properties of the concrete, the fineness of the Portland cement, you would not be able to do that without very high precision um, equipment or devices. So you need to have sort of an indirect method to estimate the fineness. And the reason that we care about fineness is that we want our concrete, our Portland cement to be uh, fine enough, because smaller cement particles, as we said, they provide more surface area. Right? Which is good, or which is generating the heat of hydration, and also it's good in terms of gaining strength. Right? So being or having fine Portland cement particles is good for the concrete. But how fine is good? We don't want too fine particles, because if we have too fine, we need to definitely spend more budget on the production. We need more advanced equipment to produce that much fineness, so it's going to be more expensive. And also can be harmful. So in terms of environmental impacts, and also for humans, it's going to be harmful, because you might inhale the very fine particles. Now, how do we measure the surface area indirectly? So surface area we can measure. So surface area can be measured indirectly, right? Because again, unless you have a very high precision scanning electronic microscope, or SEM, you won't be able to see how fine cement particles are. So the indirect method is, one of them is to let the particles flow in a liquid, and from the time it takes for the particles to travel from one point of the liquid to another point, you can estimate how fine they are. And there are also two other tests. The first one is called Blaine test. So Blaine test. It's basically the test to measure air permeability, against known standard material. Right? So you have a reference material that you know how much permeable it is, again when you try to infiltrate air through it, and then you compare that to Portland cement. You should be able to measure the fineness based on the air permeability compared to the standard material. And the second test is called Wagner turbidimeter. This is the one that I mentioned that it measures the sedimentation. So it measures sedimentation rate. Then the particles are suspended in kerosene. And that's a standard material or the standard liquid. And the concept here is that if you have finer materials, so finer particles, settles slower. Right? So imagine that you have a sort of a liquid, and then you have different types of particles in here. If you have larger particles, they take more time to settle in the liquid, and if you have finer particles, they settle faster. I'm sorry, it's actually they were around. So if you have fine materials, they take more time to settle, right? And if you have coarser particles or bigger particles, of course, they settle faster, right? So from the time it takes for the particles to settle in a standard liquid, you should be able to measure the fineness of the material, right? So that's the fineness of the Portland cement that we need to know. In terms of lab tests, we won't be able to test these in the lab, but you should be able to see, the lab instructor will be able to see, to share videos of these tests on Canvas, and you should be able to see the process for each test. Okay, so another property of the Portland cement we are interested and we want to know about is specific gravity of the Portland cement. So we want to know what is the specific gravity of Portland cement. And this is important because we need to know the specific gravity to convert weight to volume and vice versa. Because if you remember, we said that for the mixed proportioning of the concrete, we need to either know the proportions by weight or know the proportions by volume. And when you have, let's say, the proportions by weight, you should be able to convert those to volume by knowing their specific gravity. Now, the specific gravity of the cement, so G sub S of cement, typical number is around 3.15, and this is the standard for this is the number, and you probably need to remember this number because it's going to be used very often in the mix design. And this is the number that we use for, so we use for converting volume to weight proportion. And of course, the other way around. And the other definition is that we want to know the bulk unit weight of Portland cement. which is by definition that similar to what we have for the aggregates, is the weight required to fill a container. And this is highly variable for the concrete, for the Portland cement. So we can measure this in the lab based on what type of application we're going to have. And another important thing when you're designing the concrete mixed proportions, you need to know that when you are, let's say you are engineer in charge of a concrete mix design for the city or for a state DOT, let's say Caltrans, and you want to give the contractor or the concrete plant the mix proportioning, you always show the cement in terms of weight. So most of the time cement should not be measured by volume. And most of the time we measure, we specify how much cement we need in terms of bags, because the bags are standards. I believe they're 90 pounds bags, and most of the times in the concrete plants they measure how many bags they need for 1 cubic yard of concrete. All right, so those are the basic properties of the Portland cement that we can measure in the lab. But there's another important process that we mentioned we want to know about, and we talked about the chemical reaction, which is the chemical hydration or the hydration process between Portland cement and water in the mix. So hydration is basically defined as the chemical reaction between water and Portland cement. Right? Which this chemical process generates heat. And sometimes, or most of the times, this is referred to as heat of hydration. And you can easily sense this in the lab when you mix cement, the powder cement, with water. You can easily feel the heat that is generated because of the chemical reaction between the water and Portland cement. Now, why this is important for us? Because the strength of the concrete is dependent of the hydration. So the rate or the gain of the strength gain is obtained by or is dependent on hydration. Not drying. why hydration is not equivalent to drying? Because when we're talking about drying, drying means that the water is evaporating from the concrete. So we don't want drying to happen fast. So this is the evaporation of water. And then, of course, evaporation means you're going to have less water in the mix, right? Which you don't want to do that. Why we don't want our water to evaporate? Because it stops the reaction. And also, definitely, it stops strength gain. Right? So you don't want to do that. But you definitely want to have hydration, and from the heat of hydration, you can get or you can estimate how much strength you're gaining. And based on that, there is a process that by tracking the heat of hydration, you should be able to estimate the concrete strengths. And this is a process called the whole tracking process. It's called maturity test. So basically, there is a maturity index that you can correlate the heat of hydration with strength, something like this, right? So if you basically track the heat of hydration, you can estimate the strengths or the compressive strengths without doing the test in the lab. And by doing that, they should be able to, and they're already implementing that in the construction, that when, for example, you have a big slab or a foundation in the field, and you're building a concrete slab or concrete foundation, they embed these sensors, and most of them are wireless, and they are transmitting the temperature inside the concrete to a system, and from the temperature tracking, they should be able to monitor the maturity or estimate the maturity index, and also estimating the strengths after several days. So they don't need to core the materials outside of the concrete and test the sample in the lab, and they can skip that test and basically estimating the strengths based on the inside temperature of the concrete, right? Okay, so that's pretty much what we have for today.